So say we've got a surface S parameterized by RUV is x UVI plus y UVJ plus z UVK. So here I've taken a sphere using spherical coordinates. So x of, we'll use phi and theta instead of u and v. So x is cos theta sine phi, y is sine theta sine phi, and z is cos phi. So in general, when we have such a parameterization, we can consider the partials of R. So this will be del x by del ui plus del y by del uj plus del z by del uk. And R sub v is del x by del vi plus del y by del vj plus del z by del vk. So the meaning of these is that at any point, these will be tangent to the surface S. So for instance, here are those tangent vectors in our particular case. And we write those in. So R in this case, so R sub phi will be cos theta cos phi I plus sine theta cos phi j minus sine phi k, and our theta will be negative sine theta sine phi I plus cos theta sine phi j, and then no k component. So the significance of these is the following. So provided RU and RV are not parallel, they'll give a parametric description let me say at a point P. So at a point P, they're not parallel. They give a parametric description of the tangent plane to S at P. So maybe first let me just mark on this not parallel. So in our case, this is going to be the case when phi is not equal to 0 or pi. Because if phi is equal to 0 or pi, then sine phi will be 0. And so in this case, if phi were 0 or pi, then r sub theta would be 0. And 0 is considered like parallel to every vector. Okay, but so as long as that doesn't happen, a parametric description of the tangent plane at P will be given by the point P. So we move there, then we translate in either of these two tangent directions. So RV and RU at P give like the two directions we can move, and then we just move as far as we want in those directions. So previously we gave implicit descriptions or implicit equations for tangent planes, as this is a parametric description. Okay, so recall that two vectors are parallel. Do I want to? Yeah, it'll be okay to erase this, I guess. Two vectors are parallel if and only if. So RU and RV are parallel if and only if the cross product of these is 0. Here, this is the 0 vector, but we could equivalently take the magnitude and then it's if and only if the magnitude of their cross product is not 0, or is 0. Sorry. Okay, so when I said like we want our parameterizations to be somehow non-redundant, in the first lecture, this is what I meant. We want this to not be 0. So we want these to not be parallel. Okay, so definition. So a surface S parameterized by R of U and V is, we call it smooth if the partials RU and RV are continuous. They exist and are continuous, and so this will be sort of the case for any reasonable thing we write down. And more importantly, RU cross RV is not equal to 0 on the interior of the parameter domain. So like we just saw, in our case, RU cross RV can be 0 on the boundary. So in our case, the part of the boundary is when phi is equal to 0. I should write. So in our case, our parameter domain is a rectangle from 0 to, I should have done this the other way. So from 0 to pi in the phi direction, and from 0 to 2 pi in the theta direction. And this is 0 when we're on these boundary parts, but that's allowed. It's just in the interior that this has to never be 0. Okay, so if this is non-zero, then we can look at, we can consider this cross product. So what's the significance of that? So in this case, RU cross RV will be, so this is going to be orthogonal to both RU and RV, and therefore this will be normal to the surface S. So here is that cross product in the case of the sphere. And this is, I should mention, the reason I took theta or phi sub theta here as opposed to theta sub phi was because I wanted to have an outward normal. So if I took these in the other direction, if I did theta first and then phi, then the normal would be pointing into the sphere, which sometimes you want, but it's nicer to draw it pointing outwards. So this is the direction of this cross product. The magnitude, so these are RU and RV, these span a parallelogram. I should have drawn it, yeah. In our case, it's going to be a rectangle, but in general, they might not be at right angles. So the area of this parallelogram is the magnitude of this cross product. Now, this parallelogram gives a good picture of the surface near the point where we're evaluating. So we can use this as sort of an infinitesimal area. So we can use this to compute / define, depending on your point of view, surface area. Okay, so for definition, let S be a smooth surface parameterized by RUV with U between A and B and V between C and D. Then the surface area of S is A equals, so R here is our parameter domain, which is this rectangle. The surface area is the integral of this cross product of the partials with respect to area. And so then that's integral RU cross RV du dv. So U goes from A to B and V goes from C to D. And sometimes we would call this d sigma. So d sigma equals RU cross RV magnitude du dv. So this is called the surface area differential.